Good morning. I am DCAF Perez, and on behalf of my co-authors, I will be presenting our work entitled Investigating the 2019 El Niño Associated Drought from National to Local Scales Using Satellite-Derived Products. I am from the Institute of Environmental Science and Meteorology in UP Diliman, and together with our partner agencies, PAGASA and BSWM, we are implementing the Drought and Crop Assessment and Forecasting, or DCAF project under SARAI. As a tropical country with only two dominant seasons, wet and dry, we are often vulnerable to climate extremes such as drought. Understanding how it develops and impacts us is vital as it affects our food and water supply, economy, and even human health. When we look at the crop production over the last 30 years, we observe that there is a steady increase in both rice and corn yield, interrupted only with occasional dips or decline in production. Most of these dips occur during El Niño events, which drives extremely dry conditions and therefore could cause reduction in yield. At an agricultural perspective, the impacts are felt at a farm scale up to regional scales. As drought affects wide areas, remote sensing holds an important role in monitoring its development. Remote sensing is a key to large-scale monitoring as it provides information on data-scarce regions through drones, planes, and satellites from space. Spaceborne satellites launched several decades ago store long historical data of the Earth's surface which give us an idea of its climate patterns. We maximize this information to develop the means to quantify information on weather and crop health at different time scales. Through satellite data, we retrieve geophysical parameters that can serve as drought indicators and later used to derive drought indices for quantitative characterization of drought. Here, we investigate the recent El Niño-driven drought events in 2018 to 2019. Our analyses are based on these research questions that look at spatiotemporal patterns of drought development, whether it was reflected in the local climate system, and how its timing or occurrence becomes critical on crop yield. In answering these questions, we aim to investigate the 18 to 19 drought by utilizing the satellite data and verify drought events using farm and crop information. In particular, we characterize drought development during the 1819 El Nino at the country scale and local scale using satellite-derived drought indicators and indices, and we then assess the drought impacts with additional information on crop damage reports. In order to characterize drought, we utilize different variables derived from satellite products. Here, we use the estimates on rainfall, temperature, and also utilize products that look at vegetation stress and surface moisture stress. These are monthly products with a historical record of 19 to 21 years and with the recent microwave product of Sentinel with 5 years worth of data. The drought indices used here are derived from rainfall, LST, and NDVI. SPI only utilizes rainfall, while SVTR and VHI utilizes the relationship of temperature and NDVI to look at soil moisture conditions on the ground. With rainfall, we look at meteorological drought, which mostly measures drought onset, and with the VI LST indices, we look at agricultural drought as it incorporates the effects of temperature extremes to vegetation health. So using the formula for each indices, we come up with a quantification on drought stress. With this, we can identify drought signals at the country scale. The visualization and color scheme are standardized in such a way that red means stressed areas, while green is under normal conditions. For the validation of drought-affected areas, our team chose the region of Occidental Mindoro, particularly the municipality of Mamburao, where most of its rice and corn farms were affected. Standardized surveys were conducted to collect information on farm management practices and crop data during the period of 2019 to 2018 to 2019 drought. These surveys were organized together with the local agricultural officers and technicians in the area. The questionnaires are directly targeted to the farmers. For the result, first we investigate how drought developed at a country scale. So we look at its spatiotemporal patterns or its development across the landmass of the country through time. We focus during the months of January to April, which covers the growing stages of the crops planted in December and in early January. Looking at rainfall, you can see the effect of El Nino in the eastern part of the country as rainfall deficits originated in this region. The negative anomaly started in the central region of the Philippines in January, then further spread in the southern regions until it mostly dominated the northeast, central, and southern regions during February, the month when El Nino was declared by Pag-asa. On the other hand, monthly positive LST anomalies started in the western region during February to March and propagated in the central regions. With the El Nino period coinciding with the dry season, it exacerbated the dry conditions, therefore manifesting in hotter than normal temperatures. To better characterize how drought evolved during this period, we analyzed maps of the different drought indices. Looking at the rainfall-based SPI, we see drought stress during the month of February for SPI 1, which captures rainfall deviation in 1 month, while stress already occurred during January for SPI 3, which captures stress at a 3 month period, thereby signifying the extended effect of rainfall deficit. For NDVI anomaly, it mostly followed the stress pattern of LST, where it concentrated in the western and central regions in the country during the drought peak in April. Similar but more pronounced drought signal patterns are exhibited by SVTR and VHI. Persistent and severe drought can be seen in the western and eastern regions such as Occidental Mindoro and Camarines Sur, respectively, while in the north, the province of Isabela shows moderate to severe drought, and for the southern regions, Maguindanao and Zamboanga del Sur shows moderate drought signals. The pairing of NDVI with LST for SVTR and VHI included the added effect of temperature in representing dry conditions in an area. NDVI alone was able to present vegetation stress, but the added value of LST in SVTR and VHI showed more prominent stress across months, with more drought signals occurring in the northern regions starting in February. We look at the local scale to validate the drought events. The drought validation does not only look at whether the satellite captured the stress at the farm level, but it also looks at the effect of the drought timing on crops. During the last month of 2018, Typhoon Usman brought ample amounts of moisture deemed enough for the farmers to plant for the third cropping. However, after the month has passed, the dry conditions persisted until the month of April, which is the harvest season in Mamburao. This resulted in several rice and corn farms incurring 35 to 100% crop yield loss. Here in this map, we visualize the location of the farms surveyed and validated across the municipality. We also added farms that were not affected for control. These graphs show the different parameters: rainfall, temperature, and surface moisture. The parameter estimation from each validated farm were averaged and plotted across the cropping period as early as October until the harvest in April to May. Here we see that during the planting stage, conditions were fair until stress occurred during the growing season. However, the onset of dry conditions can already be felt in some farms during the planting period. Temperature anomalies peaked at the later part of the growing season, which manifested in the degrading health of the rice planted in different farms seen here. During this period, the surface moisture also declined, especially for the damaged farm relative to the undamaged ones. This demonstrates the ability of these products to discriminate stress from one affected farm to another. The timing of drought is a critical factor to consider when assessing impacts. If its occurrence falls in the water-demanding stage of the crop, then the impact would be severe, resulting in 100% yield loss. If it falls during the mature stages, there will still be yield, but it would be significantly reduced with the intense heat affecting the quality of the harvest. In this study, we were able to demonstrate just that, implying that even the satellite sees these responses on the ground. In summary, the drought investigation shed light on how its impacts depend on climate patterns, where dry regions become more vulnerable And at an agricultural perspective, drought timing becomes critical as crop stages respond differently to water stress. These findings have great impacts on farm management and drought risk preparedness. Thank you very much for your attention.